This video is an introduction to a series of videos on aerodynamics and related topics. I want to share some insights that I have gained over the years of designing and testing aircraft and just generally simulating flow over all kinds of interesting shapes. I will use the explanation of how an airfoil generates lift as an underlying topic, because popular explanations generally end up in circular reasoning or simply implying a cause by observing an effect. Let me start with a question. Does a simple explanation of lift have any value? Will it really make you a better pilot? Take this book for instance, published in 1951. Chapter 3 is on types of fluid flow. They've got this nice illustration of an airfoil, and in this paragraph relating to that illustration, in a nutshell, is the equal transit time assumption. In this context, that assumption was only used to explain pressure gradients inside boundary layers, but it did become a very popular explanation for how airfoils produce lift. There are many resources out there that will explain why this is an invalid assumption, but this is not why I'm showing you this. Have a look at the credentials of these authors. Sidney Sherby and Thomas Connolly were the guys who established the US Naval Test Pilot School. Thomas Connolly went on to command an aircraft carrier, and he became commander of the Naval Air Forces in the Pacific. He then went on to become project manager for a brand new aircraft that was being designed for the Navy at the time. That aircraft was in part named after him, the F-14 Tomcat. I think it is safe to say that that wrong assumption had no negative impact on the many generations of pilots to whom it was taught. Note that I deliberately referred to it as an assumption, not as the equal transit time theory, as it is also called. In physics and in engineering, an assumption is only ever applied in practice if it is justified with convincing experimental evidence or analytical support. You will not find the equal transit time assumption anywhere in proper theory or engineering equations. For the purpose of this video, I'm going to distinguish between fundamental laws, different types of theory, and what I consider to be a logic explanation based on cause and effect. By the late 1600s, all the groundwork had been laid in the form of Newton's laws of motion and the laws of conservation of mass and momentum. The conservation of energy would follow later. They are simple relationships or equalities that describe mathematically what we observe in the physical world. They don't explain themselves or the process that they are describing. They are the principles referred to when something is said to be derived from first principles. I'm not going to say much about thin airfoil or potential theory, other than that it is an old mathematical model for vector calculus that was adapted to produce fluid-like results. This is the theory that employs flow circulation and the famous Kuta condition. It is a fascinating tool, but it does not meet my criteria for a logic explanation of lift. This is an example of a flow field solution of the Reynolds average, Navier-Stokes, and continuity equations. They form part of the momentum theory, which also includes the works of Euler and Bernoulli. The equations are various derivations of the first principles to make them applicable to an imaginary, continuous fluid as opposed to rigid bodies. In this example, the flow is steady. Graphically, you can easily identify the relationships between pressure and velocity, or between flow curvature and pressure gradient. But these relationships only describe the flow as it already exists. You could argue that in nature, force is the cause, and any change in speed or direction is the result or the effect. Therefore, in the context of flow, pressure or pressure gradients must naturally be the cause of the flow curvature or the velocity at any point. But how do you distinguish between the greater pressure fields being the cause of the pressure at the airfoil? Or is it the other way around? The problem is that a developed flow field gives no clue about how pressure is communicated from one position to the next, and this is the process that I hope to explain. There is a lot that can be learned from particle collision models, but the key concepts are the following. A particle colliding head-on with a large object is going to absorb energy and bounce away faster, distributing that energy among nearby particles it collides with next. The opposite happens on the rear of the large object. A particle colliding with a receding surface will transfer energy to that object, lose some of its own kinetic energy in the process, and in turn absorb energy from the surrounding particles. I am still busy developing this simulation program. I will go into much more detail in the future video. Now, how does this help us understand flow at a macroscopic scale? I'll use an ellipse just for some variety, and let's bring back time into the picture by first considering the ellipse at rest. How do we get it from this to this? I ran a simulation with incredibly small time increments to capture the process just as the ellipse starts moving. The simulation is for a stationary ellipse in moving air, but the relative movement is so small you can just as well imagine that it's the ellipse moving into still air. There are some interesting things happening at the trailing edge, and it actually produces decent lift despite the area of flow separation. For an airfoil, the flow develops in a very similar way. The sharp trailing edge limits how far that initial rear stagnation point can creep forward along the top surface before getting pinched off just as the trailing edge vortex is shed. That trailing edge is 2 millimeters thick on an airfoil with a 1 meter chord length. It is a very dynamic process that plays out in just a fraction of a second. Some aspects of the simulated scenario are unrealistic for various technical reasons, but the results offer a glimpse into a basic sequence of processes through time. I think it is a bit more intuitive if I explain it in terms of an airfoil moving into still air. There exists an interaction between the air and the surface at all times, even at rest. This interaction changes the instant the airfoil starts moving. How this new interaction affects the surface pressure depends on the slope of the surface at any particular point. Initially, any forward-facing part of the surface sees a rise in pressure while the aft-facing slopes experience a pressure drop due to the molecules impacting a retreating surface. A more accurate pressure field should look like this, where you can better see how the pressure varies with the slope of the surface. This is the leading edge of a symmetric airfoil at zero angle of attack. Now, if the airfoil had to stop moving right here, this pressure front will just spread out and dissipate like a pulse of sound. But the airfoil keeps moving, which means it now flies into this affected air, and this leads to different relative velocities between the surface and the air molecules, and therefore another change in the pressure along the surface. While this is happening, the different pressures inside the affected layer of air starts creating flow along the surface. Again, this means new relative velocities and further change to the surface pressure. This is how the flow field is created from the airfoil surface outward, and it makes sense to phrase it like this, because ultimately it is only the presence and speed of the airfoil that results in the flow field existing at all. But how does the greater flow field affect the airfoil? By now this should hopefully be a little bit more obvious. The airfoil created a pressure disturbance which spreads outwards, and now the airfoil flies through that disturbed air. At some point the flow field reaches a state where the disturbance is such that when the airfoil flies through it, it results in exactly the same disturbance, just repeating the cycle. That is why I explain it in terms of still air with an airfoil moving through it. It makes it easier to visualize the airfoil radiating this field of influence out ahead of itself and then flying through it, only to be affected by its actions from a moment earlier. It is not quite as easy to visualize what happens behind the airfoil, but it is exactly the same. The airfoil is flying away from the air behind it, which affects the air at the surface. That change gets distributed all around, and now the airfoil flies away from that, repeating the process. The same goes for air above and below. It is important to point out that this entire process depends on air being compressible. If air is assumed to be incompressible, then speed of sound is infinite, and any change in surface pressure is felt instantaneously all around, while the greater flow field instantaneously affects the airfoil in return. But when you introduce compressibility and a finite speed of sound, you get a better idea of the time delay that exists between the change in pressure at one point and its influence being felt somewhere else. I created the simulation to help demonstrate how pressure influence is communicated. Again, the simulation plays out in super slow motion, so it makes no difference whether you choose the airfoil or the air as the fixed frame of reference. Within the developed flow, I'm going to trigger a pressure pulse. It represents a small parcel of air undergoing a change in pressure. Just like at the airfoil surface, any change to the state of air anywhere in the field subsequently affects the air around it in all directions. All I'm doing here is magnifying the influence of this particular parcel. As that parcel changes pressure, it affects the air around it, and that change is felt further and further away over time. Eventually it reaches the airfoil surface and is reflected back, but now slightly modified by the fact that the surface was moving. I think repeating the simulation with the airfoil traveling at close to the speed of sound, or even supersonic, should be quite interesting. Here I have two pulses, one positive and one negative pressure. Where the two pulses cross each other, you get destructive interference, but ultimately each pulse continues to spread outwards. The pressure at every point in the flow field is therefore the superposition of all the pulses from every other point that happen to pass through that point at that time, and that is even true for still air. And now for the anticlimax. What I have just described so far is not something that is special to airfoils, but applies to anything moving through air. If this is making you scratch your head right now, well, that is how air gets around your hand on its way to your head. It happens around airfoils whether they are producing lift or not. To produce lift, we need to somehow ensure that the pressure on top is lower than at the bottom. It is necessary to introduce some asymmetry to the pressure field. Actually, for a single airfoil, the asymmetry in the greater field is not our concern. We have no control over it other than via the pressure on the airfoil surface. The detail of how that comes about requires a closer look at how the curved surface along an airfoil interacts with molecules flowing along it, and how you can control it by using a sharp trailing edge. I will leave this until the next video, along with a look at the molecular nature of viscosity and flow separation.